Peeling back the matrix, the chemical architecture of high press.
Modern laminate flooring can achieve AC5 wear ratings, shrug off standing water, and survive direct, heavy impacts. This performance is the result of a highly specific multi-resin chemical architecture hidden beneath the wood grain texture. These surfaces are engineered composites, constructed from multiple layers of resin-saturated paper that are fused into a rigid, non-porous solid. If we pull apart a sheet of high-pressure laminate, or HPL, we find three foundational components. On top is a transparent alpha cellulose overlay, sitting above a printed decorative paper layer. Below that sits a dense core made of 6 to 8 sheets of Kraft paper. Getting these distinct paper layers to act as a single high-impact monolith requires pairing two very different thermosetting polymer chemistries. Manufacturers use phenolic resins to bind the deep core layers and melamine resins to seal the surface. To understand how these materials actually work, we have to deconstruct the specific condensation networks of these layers. We need to analyze the intense thermomechanical physics required to fuse them together and look at the cutting-edge Vitromer polymer networks currently being designed to make these permanent thermosets fully recyclable. Mastering modern lamination means navigating both the exact molecular chemistry of the individual resins and the severe mechanical engineering necessary to synthesize them under pressure. Let's start with the bottom of the HPL stack. The deep core relies on phenolic resins, or PF. This is the absolute foundation of industrial-grade lamination. The chemistry here traces its roots straight back to 1907, when Dr. Leo Baekeland managed to stabilize the reaction between phenol and formaldehyde, creating Bakelite, the first truly synthetic thermosetting plastic. Today, PF resins are explicitly chosen to saturate the Kraft paper substrate because they impart exceptional mechanical toughness and extreme thermal stability to the finished board. This diagram shows the synthesis of PF via the condensation of phenol with formaldehyde. Depending on the catalyst used, manufacturers navigate two distinct chemical pathways. On the left, an alkaline catalyst pushes the reaction down the resins pathway, creating a one-stage resin. It is entirely self-curing. The application of heat forces it into a fully cross-linked network. On the right, an acidic catalyst creates novolacs, thermoplastic prepolymerase. Heat alone won't cure them. They require an external curing agent, like hexa, which acts as a chemical bridge locking the chains together. This dense cross-linking gives the laminate a rigid structural backbone. However, the chemical process naturally leaves the resin a dark reddish-brown color, which completely rules out PF for any light, decorative surface applications. For the decorative face of the laminate, we have to switch chemistries entirely and move to the top layers of the stack, utilizing melamine formaldehyde, or MF. Fully cured melamine yields massive physical advantages. It provides extreme surface hardness, making the laminate highly resistant to physical abrasion, while remaining completely chemically inert against common household solvents and acids. Crucially, unlike the dark phenolic core, the polymerization of melamine produces a highly transparent finish. This optical clarity allows the high-fidelity printed patterns on the decor paper below to show through exactly as intended. To get the resin into the paper, manufacturers rely on the fact that uncured MF is completely water-soluble. This allows the clear, viscous prepolymer to deeply impregnate the porous decorative papers and the top alpha cellulose overlay. Once cured, this top melamine layer acts as the primary environmental shield. It transforms a structurally sound but vulnerable core into a viable, damage-resistant surface capable of withstanding temperature exposures up to 180 degrees Celsius. We now have an impregnated phenolic core and a melamine surface layer. The manufacturing challenge is physically fusing these two disparate chemistries into a single composite that will not delaminate under stress. This technical table compares the parameters required to fuse different laminates. Looking at the high-pressure laminate column, the process demands massive force. The stack is subjected to pressures up to 1,500 psi, held at 150 degrees Celsius for an hour. Under these extreme conditions, the uncured resins begin to flow, physically interpenetrating the fibers. They undergo a highly exothermic cross-linking reaction, cooling into a single monolithic sheet. We can contrast that intense process with low-pressure laminate, frequently called thermally fused melamine. The LPL column reveals a far more streamlined process. Pressures drop drastically to the 300 to 500 psi range, running at slightly higher temperatures to achieve an exceptionally fast cure time of 30 to 60 seconds on a single paper layer. Because LPL construction omits the thick phenolic core entirely and relies on lower pressing forces, the finished material is incredibly thin, usually between 0.1 and 0.5 millimeters, resulting in significantly lower impact resistance. The physics of the manufacturing environment, specifically the pressure gradient applied during curing, dictate a laminate board's final wear rating and end-use application just as strictly as the resin chemistry itself. Executing those thermomechanical parameters requires precise hardware. Uniform resin flow and high-fidelity surface textures rely entirely on the engineering of the mold and press plates interfacing with the laminate stack. The metallurgical requirements for these press plates are severe. Industrial suppliers typically utilize specific high-grade alloys like SS630 stainless steel. To survive tens of thousands of intense pressing cycles without warping, these plates are heat-treated to a hardness of 40 to 45 Rockwell C. They are then hard chrome plated up to 70 HRC to ensure the micro-textures pressed into the wood grain finish don't degrade over time. If a plate is imperfect, you risk creating dry spots. This happens when uneven pressure prevents the liquid resin from flowing properly, resulting in uncured sections and guaranteed structural failure. To prevent this, tooling engineers deploy specialized press pads between the heavy metal platens and the steel plate. Manufacturers often utilize pads made from a specific composite of silicone and copper wire. The dual material design is highly intentional. The silicone flexes to equalize physical pressure across the entire surface, while the highly conductive copper threads ensure perfect, uniform heat transfer down into the resin stack. Achieving that perfect lamination bond is an exercise in interface physics. If the physical heat transfer across the tooling matrix fails by even a fraction of a degree, the underlying polymer chemistry simply cannot successfully cross-link. But the same permanent bond that provides this material's longevity is also its greatest flaw. Once these thermosetting resins cross-link, the entire chemical network is locked. The material will char and burn before it ever melts, making it effectively impossible to recycle. Combine that recycling gap with strict new environmental mandates targeting volatile formaldehyde emissions, and the industry is being forced to actively move away from its traditional phenol and melamine precursors. The immediate transitional step is replacing petroleum-derived chemicals with bio-based alternatives. Manufacturers are currently substituting synthetic phenol with Kraft lignin, extracted from wood pulp, and deploying plant-based epoxidized soybean oils to maintain strength without the toxic byproducts. To solve the recycling gap, engineers are developing vitrimers, a new class of covalent adaptable networks. Under thermal or UV stimuli, their rigid bonds temporarily detach, slide to new positions, and instantly relink, allowing the material to alter its geometry while remaining fully connected. This shift in network topology allows a fully cured laminate composite to be reshaped, repaired, or even cleanly depolymerized for chemical recycling. By engineering covalent adaptable networks, the industry is combining the thermomechanical durability of a traditional thermoset with the sustainable circular recyclability of a thermoplastic.